All right, so what you see in front of you today is a little worksheet to kind of review sort of where we have been so far. And so, kind of keeping in mind of what we've really talked about, all of this is kind of relating back to work. And if you remember from our original equations on here, work is going to always be related to the change in kinetic energy. So we know that. We know that kinetic energy is equal to 1/2 mv squared. Sorry for the bad writing here, using kind of a weird little pen. And then within this, we started to learn a little bit, okay, well, what if we look at the rate of work or how much work is being done over time? And that's kind of where power came in. So, power is really about this change in energy over time, which we can often refer to as just the work over a given period of time, which is how we get our joules per second, aka our watts. And so, if you really think about what we're looking at, we're not adding too much to this. We're talking about, how if the force is changing, we look specifically at work, we start talking more about energy. And then if we think about how much work is being done in a given amount of time, that's where power comes into play. That's where the watt comes into play. That's where watt hours come into play. All these things on here. So I just wanted to really quickly talk about like the ways in which I would approach problems like this, and then let you guys have the rest of the time to kind of knock out this worksheet. So we're reading this first part. Child pushes a small toy lawnmower along the ground with a force of 30 degree. Okay, cool. So child starts walking the sidewalk. We're at rest. The net force. Got it. So I got all this information about this child pushing this lawnmower. And the first thing he wants you to do is draw a free body diagram for the lawnmower when it has the displacement. Now, what I don't like about it says draw the free body diagrams. Like there's more than one. And that honestly confused me at first. And so when I was talking to Mr. Connell about this worksheet, he said, yeah, there really is only one free body diagram, but you could talk about changing the arrows based off what's happening on here. So I'm going to diverge on this a little bit and just kind of create this free body diagram so we can sort of see this child. All right, so this child is applying a force of 30 degrees relative to the right. So I'm going to have this applied force kind of go in that way. So FA, and we can say, all right, there's theta right in that spot. And then everything else that kind of goes into play, well, we're going to have force gravity down. We're going to have force normal up. And then I'm going to assume there's some kind of sort of opposing force because the force is changing. And I'm going to say that opposing force is acting opposite motion, and that would be my force of friction. So remember, when we are creating free body diagrams, you do not want to include those components into your actual diagram. This will just sort of help us see what is happening as we go from one spot to the next. The reason why they wanted free body diagrams is because if you look at the displacement between 1 and 4, force is changing a lot. We're starting at 6, we're dropping down to a net force of 0, and then we're dropping to a net force of -4. Now, what's really weird to look at all this is that, yes, we have this net force, but we have positive displacement the entire way through. And so if you really think about this, the net force is going with the object in the positive direction, and it's a really strong, I guess, high level force of 6 newtons. But by the end, the child is still progressing for a displacement. Now we have no value of time on here, so we don't really know how long this is taking. We just know the total displacement and the force. So as you go further through with this graph is a little bit weird to look at and try to figure out like what does this actually like mean as the child walks through. And I think this first section is probably the easiest section to visualize because it's just a force of 6. Like we have the child is pushing the little lawnmower and it's moving in the same direction with a net force of 6. And then all of a sudden the force drops almost from like 1.5 meters to 2 meters. And you're like, well, why would that happen? And if we look back at our free body diagram, if the force is dropping, I would say initially, if we look at our components on here, we're talking about the force being applied in the x direction because the child's kind of walking along here. So we really only care about, the component of the cosine with this force applied. Let's suppose this child, who is pushing this lawnmower, which has this weight on here, all of a sudden just decides to stop pushing it as much. Well, if it doesn't push it as much, you would assume, okay, well, friction is going to start to take over. That's sort of where this drop comes into play. So this is like, okay, child, I'm kind of losing focus, and maybe I'm not pushing quite as hard as I would. And so because I'm not pushing quite as hard, friction starts to take over. There's less of a net force. It decreases until the net force is 0. And you may say, well, how on earth can you have a net force of 0 and still actually have positive displacement? Well, think about that. Net force of 0 just means acceleration is 0. So this child is no longer accelerating the object. Friction and the force applied are in an equilibrium situation. So we definitely can still have positive displacement. And so as we look at this, we're, net force 6, we're pushing. Got this really big arrow in this case, right? We're pushing this on here. And then maybe we're not pushing quite as much, but we still are overcoming friction. And then all of a sudden we reach an equilibrium where the component in the x direction and force of friction are the same. And then you're like, well, what about this bottom section then? This is weird. We have net force negative. How can we still be going in the positive direction? Well, the short answer is we're slowing down, right? So if we have a net force in the negative direction, remember force is equal to ma. And so if this is negative, your acceleration is negative. That just means in this little section down here, the child is pushing so lightly that friction is sort of taking over and they're not accelerating. Because really in this first section, this is pretty chaotic. This kid is flying. You got net force of 6 in this case, and this kid is accelerating like crazy, and all of a sudden, not accelerating quite as much, no accelerating, and then actually negative acceleration or slowing down. So keeping that in mind will help you to sort of analyze what this question is really asking you to do. And so when you talk about this free body diagram, it's just really representing these different arrows. So between which displacements is the net force acting in the same direction as the motion of the mower. So I think you can kind of visualize that. Our net force is positive. Our net force is still positive. So I would say that the net force acting in the same direction as the mower, is going to end up being between, 0, displacement of 0. So I'll put x in the middle there, and 2. Because we have our net force positive and then going in the positive direction. How is the velocity of the mower affected by the net force in the same direction as the motion? So how is the velocity of the mower affected by the net force acting in the same direction? So we kind of already said this as well. You'd be accelerating, so you'd expect your velocity to be increasing. Here's the part where I want to talk a little bit more, though. During which displacement intervals is the work positive, negative, 0? There's an easier way to do this than what we just kind of said. Now, we could talk all about force and, the displacement and kind of look at it from that perspective. But if you remember, force times displacement is how we actually figure this out for our actual work. But in reality, work is the integral of force relative to displacement. And that ds means displacement. Don't worry so much about that. Since it's the integral and we're talking calculus, we can do the area under a curve. Now, our horizontal axis is right there. And so if we're looking for net work of 0, we can see right from these little sections, there is no area under the curve. Force by distance, we could really just say, oh, okay, between 2 and, 3.5, we'd say there's really no work being done on this object. And then obviously positive work is being done because we have the area under the curve that's above the axis in that first section, and then negative work is being done in that second section. So describe what happens to the motion of the mower between 1.5 and 2 meters. So 1.5 is kind of this section, and 2, this object is still accelerating. We have a net force. It's just, not accelerating as much. Acceleration is changing. And so we could calculate the net work being done, or the work being done there, by doing the area under the curve if we really wanted to. This object's still going forward. It's just not going forward as much with as much acceleration as it was from initially. And then calculate the work done on the mower from 0 to 2. That's just an area under a curve calculation. I feel like you guys can do this. Now remember, this is a triangular section when you calculate that on there. Calculate the work done from the mower from 3.5 to 5.5. So 3.5 to 5.5. This is the area under the curve in this section. Got a triangular section right there. And we got a rectangular section right there. Keep in mind, it is below the axis, so this actually will be a negative value. And last but not least, we tie this all together. If the lawnmower has an initial speed of 2 meters per second, determine its final speed. Now, this is going to be a little bit trickier because you have to think about the idea that work and the entire system is our change in kinetic energy. Now, we do actually know the weights of the lawnmower. That's the weight, though. It's not the mass. And so if we're talking like K final minus K initial, I do know it's 2 meters per second, and we know that K is 1/2 mv squared. You'll have to do a little bit of work here. We know the V. Figuring out the mass is going to be a little bit tricky because that's not mass, that's mg. That's actually force gravity relative to the mass on there when we talk about the weight. So that would be 39.2 would be equivalent to the mass times 9.8. So you have to kind of work backwards, figure out the mass that lawnmower is. Now, In order to do this, we'd have to actually figure out, okay, what is the total work done on this system? We have some positive work, we have some negative work, we have some zero work. And so as you go through this to try and figure that out, you're kind of adding up these little sections and then solving for, within this K final, what is the V final? And so it's not too crazy. I think it gets the basic point across, but I wanted to just kind of break down this graph so you kind of see this. Anytime we have a graph, we're looking for one of two things. We're either looking at the slope of the line or we're looking at the area under the curve. I think that should be enough to help you guys try and knock out the rest of the worksheet.